Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at a fundamental result, really, one which we've already seen before in video 1 in the series on differentiation, no less, which is when we have x to the n as a function, and when we differentiate it, of course, we get nx to the n minus 1. However, we want to now prove this result for n actually being a real number. As I say, we've seen this result before, but we saw it in the context where n was a natural number, and at that stage we used the definition of differentiation and the binomial theorem to be able to prove this. But today we're going to basically use other arguments to be able to prove the same result, but now in the case where n is any real number. So let's get started. So we start by just taking our function, and what I actually want to do is I want to use ideas of logs to be able to manipulate this and then use some of the machinery that we've actually developed in the theory of differentiation to be able to arrive at our result. But I've got to be very careful when I'm taking logs. You can't really take logs of negative numbers, okay? So in order to sort of take logs in a systematic way, which is, well defined, I've got to basically consider cases. So let's take a look at case 1, and case 1 might be where I take x to be positive, right? So when x is positive, then I can see from this sort of function that actually y is also going to be positive because it doesn't matter what n is. When you take a positive number and raise it to any power, whether it's positive or negative, you're going to get a positive answer, right? So it tells me that y is positive uh, where n can actually be any real number, okay? So now, since I have my x and y as both being positive, then what I can actually say is I can actually come to this expression or this function, and I can say we can just take logs of both sides. So let me take the natural log of the left-hand side and let me take the natural log of the right-hand side, right? And this is, of course, well defined for n being any real number. And indeed, once I've taken logs, I can actually go further and I can apply the sort of parachute property of logs, which is to say, the power on the thing on the inside can sort of come down like someone jumping out of a plane with a parachute. So again, this property is actually true for all real numbers. So at this stage, what we do is we basically differentiate, right? So we implicitly differentiate. And we've seen this lots of times before, so I'm just going to sort of write this down. We differentiate the left-hand side with respect to x, and as a result, we have to do the same to the right-hand side, otherwise our equation above would not be balanced anymore. But of course, when we do this, the left-hand side is actually a function of y, so to be able to differentiate it with respect to x, what we actually have to do is actually differentiate it with respect to y, and then multiply that by the derivative of y with respect to x. This is just using the chain rule, no less, right? And the right-hand side, well, this is sort of straightforward because our n is just a real number, so, differentiation leaves real numbers alone when it's multiplying an entire function. So I can just bring that out and I can just have that. So I've just tidied things up to be able to make the most of the space that we actually have. So when we have this, obviously, we need to go and sort of differentiate each part. So when I differentiate a log function, I know I'm just going to get 1 over, so I'm just going to get 1 over y, and the dy by dx would just come along for the ride. And of course, the n is just any real number, so that's just going to be there, and the log x is going to differentiate to give me 1 over x, right? So I need to say that n can actually be any real number. Uh, so at this stage, we really just rearrange this and we say dy by dx is just n times by 1 over x times by y. But we actually know what y is, right? We sort of started out with our definition for y. So we can actually come back and say it's going to be n times by 1 over x times by x to the n, okay? So indeed, by applying sort of rules of indices, we can just say it's just going to be n times by x to the n minus 1. And so far, since all of the working we've done is actually for n being any real number, then we can say, therefore, the result holds for x and y being positive and n actually being any real number. So we've actually proven our result in part. So now the only thing we're required to do is to go back and actually prove this result for x not being positive but x being negative. So let's make some room and let's have a go at that. So case 2, when x is actually negative, things actually sort of get out of hand somewhat. Which is why in the previous sort of case, I did not talk about the statement actually being a theorem. I rather wrote down a question and just wanted to sort of think through as to what would happen if n was a real number. So let's actually think about this. So if x was actually negative, and if n was a real number, the problem actually is y equals x to the n is not actually always defined, right? Which might come as a surprise to you, but perhaps if you actually consider some of the examples I've sort of laid out here, things will start to make a bit more sense. So of course you shouldn't be surprised if I go away and take, say, -4, which obviously is negative, so x is less than 0, and since we want n to be any real number, I can pick n to be a half, and straight away we see that x to the n just becomes -4 to the half, and this thing here is not defined in the real system because we can't take square root of negative numbers in the real number system, right? So straight away we found an example where this thing here is not defined. But actually it gets worse than that because there are infinitely many examples like this, okay? So another example might be, let's just say pick x equals -5, right? So when we pick x equals -5, of course x is less than 0, so that's fine. And then we can say take n to be negative root 2, right? So n in this case obviously is a real number because root 2 is a real number, and so is negative root 2. But if you go and put that in your calculator, which is basically substituting the values for x and n, you will find that you'll get math error, right? Or maths error, as we say. So again, this function is not actually defined for negative x in this case. On the other hand, there are certain values you can pick where x is negative, where that function is perfectly well defined, right? And a good example of that is if you take x to be, say, -8, and in this case, obviously, -8 is sort of less than 0, and you can go and take n to be, say, a third, even minus a third, right? That doesn't really matter. And what you will find is when you go put that into y equals x to the n, you will actually get some sensible numbers coming out of it. So the general message is we actually need to be very careful when we're dealing with y equals x to the n for n actually being any real number and x being less than 0 in particular. Okay? So I have a general statement here which gives you an idea that actually infinitely many cases are going to fail. So let's see what it says. It says generally y equals x to the n is not defined for x being negative and n being some fraction where the fraction written out has to be in simplest form. So in other words, you can't cancel parts of k with parts of L. In other words, they share no common factors. And in this case, we want L to actually be an even number, okay? So what we're saying is if L is an even number and K and L are in simplest form and X is negative, then actually Y equals X to the N cannot actually be defined, okay? And we can just sort of check this directly. So if X is negative, we can say, let's define a new number called capital X, and we're going to make that positive, so our lowercase x can just be negative of capital X, okay? So if the capital X is positive, then all of this has to be negative, so x is actually negative. And n equals k over L, well, if L is even, that means there exists some L prime such that L is actually two lots of L prime, making L even. And then what we can do is we can go to the definition of y equals x to the n, and we can basically substitute for what x is and for what n is. So my lowercase x is going to be negative uppercase x, and my n is basically going to be k over L, but my L is basically 2L prime. So my n is actually basically going to be k over 2L prime, which is exactly what I have here, right? But the minute I write something like that down, just by using rules of indices, I can sort of massage this, and I can rewrite this as negative x all to the power of a half, and then the whole thing to the power k over L, right? So when you sort of expand this out, you'll get back to this. So this equality is completely sensible, but here we have it. We actually have a problem here. The problem we have is we've now got a generic description where we're trying to take the square root of some negative number, right? How do I know that number is negative? Well, because x is guaranteed to be positive. So just that x by itself is positive, and then it has a negative out at front, which means negative x is always going to be negative. So we cannot actually take the square root of this number, which means this thing on the inside is not defined, which means the entire thing is not defined, which means y equals x to the n is not defined. So we've constructed a situation where infinitely many things of the form y equals x to the n are actually not defined when x is negative. And indeed, in this case, our n was actually a rational number. If our n is not a rational number, so in other words, it can be an irrational number, things actually get even worse in some cases. So the message to take away from this is we've got to be very careful about what we do with x being negative when y equals x to the n. Okay, so the way forward here would be actually to consider a special case. So the special case we can actually consider is we can say, okay, we still take x to be negative, but let's now restrict our n to be just integers, so just positive and negative whole numbers. And you'll see that in this case, we actually can go and sort of do our differentiation thing and get the same result that we wanted to. So in such a case, when x is actually negative, what we're going to have is, of course, y is x to the n, but if n is even, then any negative number to an even power is actually going to give me a positive number, right? So when x is negative and n is even, y actually has to be positive, and similar sort of thinking will tell you that when x is negative and n is odd, y then actually has to be negative. So really, what we can do now is we can just consider sort of sub cases. We can say, let's take sort of case this one here where n is even. Then we end up with x is negative and y is positive. So I again go back to my y equals x to the n, and I actually want to say since x is actually negative, then we can define x to actually be negative x, where capital X is actually positive, right? Which means that the lowercase x is always going to be negative. At this stage, we basically say since y equals lowercase x to the n, that's the same thing as y being equals to negative uppercase x all to the n, but we can redescribe sort of negative uppercase x as negative 1 times by uppercase x. So this whole thing has to be to the power n. But using basic sort of rules of indices, we can actually come and say this. Because n is even, then we know that negative 1 to the n is actually just positive 1, which means our y can actually just be written as uppercase x all to the n, right? So the important thing here is that my uppercase x is actually positive and my y is actually positive, and the fact that my n is even, well, that's just something we know from the way we've set this up. So now using the result from case 1, because if x and y are both positive and n is even, then that's the same thing as saying x and y are positive, and actually n is allowed to be a real number because every even number is a real number. So I can use the result we've proven in case 1. So I can say dy by d capital X is actually just going to be equals to n x to the n minus 1, where of course my n is any sort of even number. So one might think that we're sort of done here, but we're not quite done because the function that we were actually dealing with was this one here. And the function that I've actually proven something for is actually this one here. So we need a way of being able to re-express this in terms of dy by d lowercase x, right? And how we're going to do that? Well, we're going to use the chain rule. So I'm going to say dy by d lowercase x is the same thing as dy by d uppercase x times by d uppercase x by d lowercase x, okay? So we already know dy by d uppercase x, so we work out d uppercase x by d lowercase x, okay? So since we know that lowercase x is negative of uppercase x, that's the same thing as saying uppercase x is negative of lowercase x, and then that tells me directly that d of uppercase x by d of lowercase x is just negative 1. So we've actually even worked out the second thing, and so we can actually just substitute. So I can say dy by d lowercase x is basically going to be n uppercase x to the n minus 1 times by negative 1. And of course, I want to get rid of the uppercase x, so I'm going to use this description. So I'm just going to say this is exactly the same thing as n times by negative x to the n minus 1 times by negative 1. and using the exact same idea that I actually used earlier, which is I'm going to split the thing on the inside up as follows, and then I'm going to use the fact that I can distribute the power as follows. And at this stage, we notice that actually this thing here and this thing here have the exact same base. And I should perhaps put the power in here explicitly. And so what I'm going to have is I'm going to have these powers being added up. N minus 1 add 1, I just end up with n. So I actually end up with n times by negative 1 to the n times by x to the n minus 1. So since our n is actually even, then as before I'm going to say negative 1 to the n is actually 1, which then tells me that my dy by dx, and this is lowercase x obviously, it's just going to give me n times by x to the n minus 1, because this thing here is just 1, right? So we've actually managed to prove our result in case 2a for n being even. So let's now go and take a look at case 2b. So in case 2b, obviously, as we've already seen, that we're going to have x and y both being negative, and n is actually going to be odd. So since the function we want to be dealing with is y equals x to the n, as before, what we actually want to say is we want to define the following. So we want to define our lowercase x to be negative of uppercase x, where our uppercase x is positive. This would guarantee that the lowercase x is always negative. And we want to define the lowercase y now to be negative of uppercase y, with again our uppercase y actually always being positive, which will guarantee that the lowercase y is actually negative. Okay, so once we've actually got that, then what we actually have is we're going to have a situation where our, let's do it here, we're going to have y equals x to the n is actually going to give us the same thing as negative capital Y is actually going to be negative capital X all to the power n. And sort of using the same sort of ideas from before, we can sort of split this up as follows, and then we can sort of split this up even further and distribute the power. And since n is actually odd in this case, then what that tells us is that negative 1 to the power n, any negative number to an odd power would actually give us something negative. So what that basically means is, so that is what we actually end up with, the statement negative y is equals to negative 1 n x to the n actually is the same thing as negative 1 times by x to the n, and the negatives are actually going to cancel to give me y equal x to the n, right? Where our x is positive, our y is positive, and our n can actually be any odd number. So now this is a much better situation because we can handle this, right? So I can go back to my case 1. Why can I use case 1? Because I know both my x and y are positive, and because n is odd, then it's necessarily real, right? Every odd number is real, so I can actually use my result in case 1, and I can say d capital Y by d capital X is n capital X to the n minus 1, and of course, this is true for n being odd numbers. So we've effectively proven what we actually wanted to prove, but the slight catch is we want to do it for the function y equals x to the n in the lowercase, and we've sort of done it for the uppercase. So we need to be able to convert this and re-express this in a suitable form. So what I'm actually going to do is I'm actually going to start with my description of y, and then I'm going to say, let me differentiate both of these sides with respect to lowercase x. Why do I want to differentiate both of these sides with respect to lowercase x? Is because when I actually do that, then the left-hand side actually gives me the thing that I'm looking for, and the right-hand side gives me a chance of being able to use that sort of thing that I've already worked out. Okay? So once I've written that, by the chain rule, I can actually say this. So I can say that's the same thing as d of negative y with respect to capital X times by the derivative of capital X with respect to lowercase x, right? We know from earlier that lowercase x is actually negative of sort of capital X, and that tells us that capital X is negative of lowercase x, and that tells us that the derivative of capital X with respect to lowercase x is actually just negative 1. So we've actually worked this thing here out. So we only need to figure out what this thing here is going to look like, but that's not that hard because we know that if we've got a function like, say, a times by f of some function of x, and that's some capital F, then we know when we differentiate capital F, we can actually just sort of differentiate the lowercase f, and the a just comes along for the right, doesn't it, right? So the same thing is actually going to happen here, which is the -1 in front of the y is actually just going to come along for the ride, and so we can just pull that out, okay? I mean, it might be more sort of apparent if I actually describe this in Leibniz notation. So in Leibniz notation, if I have a derivative like that, then the answer is going to be the exact same thing as a derivative like that, which is of course the exact same thing as that sort of thing here, which is precisely what we've got here, right? So we know that when we have a number in front, we can just pull the number out and differentiate the function on the inside, and that's precisely what I'm going to do here. So I'm going to pull the -1 out and just differentiate that y on the inside, so I actually end up with this thing here. So once we've actually got this, now we're nearly home, aren't we? Because we actually already know what this is, and as I've already said, we've already worked out what this is. So we just substitute things in, right? So we get dy by the capital X is just going to be n capital X to the n minus 1, and there's a -1 out already, and then the capital X by the lowercase x just actually gives me -1, doesn't it? Okay, so when we simplify that, we just end up with n capital X to the n minus 1. So all that's actually left is for us to be able to replace the capital X with the lowercase x. Let me make a bit of room, and then I can sort of do that. This is much better. So what we can say, it's n, and then my capital X is just my negative of lowercase x, and then the whole thing is to the power n minus 1. Okay, so again, splitting this up, I can just say it's -1 times by x all to the power n minus 1, which is the same thing as n times by -1 all to the power n minus 1 times by x all to the power n minus 1. But the beauty now is, since we know that n is actually odd, that tells me that if I take one away from an odd number, I better get an even number. And that tells me that actually -1 to the power of an even number is actually just going to give me +1, which means I can actually come back here and just put this result in. So it's going to be n times by 1 times by x to the n minus 1, which of course is nothing other than nx to the n minus 1. So we've now been able to work out exactly what we were after. And so we've actually managed to sort of prove our special case for n actually being any positive or negative whole number, and x actually being negative. So I think that's probably a good place to stop. Thank you for watching. If you found the video useful, then please do hit the like and subscribe buttons. That's a really good way for sort of new people to find the channel and to find the content. Do let us know in the comment section as to what you would like to see more videos on. And as always, we will see you in the next video.